Hi, my name is Sam Cheyette, and you're talking about a project where we've been trying to understand the perceptual mechanisms underlying number psychophysics. So, the history of number psychophysics begins with this guy, William Stanley Jevons, who was primarily an economist and political theorist, but also spent some time counting beans. And he asked in an 1871 Nature paper, how many objects can you apprehend in your mind, can you hold on to in your mind at once? And what he did to answer this question was he threw beans repeatedly into a bucket and yelled out how many he saw every time, and recorded them in this table, where the actual number of beans that were in the bucket is on each one of these columns, and the numbers, possible estimates, is on the rows. And he recorded how many times he saw each one of those pairs. So there's two kind of observations that he made. One is that the answer to his question, how many objects he could hold in his mind at once, was 4. After 4, he started to make some errors. And in fact, the magnitude of his errors increased roughly linearly beyond that. And curiously also, he tended to underestimate larger quantities. So why is this? What explains these psychophysics? So one potential answer is that there's, and this is kind of the commonly held view, is that there's these two systems that are at play that kind of you see for small and large magnitudes. So this Tix paper in 2004, Lisa Feigenson and colleagues write, performance signatures common across development and across species implicate one system for representing large approximate numerical magnitudes, and a second system for the precise representation of small numbers of individual objects. So in this view, there is a large number system, called the approximate number system, which noisily represents ensembles. Kind of the hallmark of this system is that discrimination ability is ratio dependent, which is also called Weber's law. And one way people commonly represent this is that the approximate number system has linearly increasing standard deviations of noise in the representations. So small quantities are represented less noisily than larger quantities. And the second system is the parallel individuation system, which is also called subitizing, and this is kind of a discrete system that's thought to rely on attention and object tracking mechanisms. So this system does not have that same property of increasing error. This is just a discrete system for kind of holding on to objects discretely, and so there's actually no error at all. And the explanation for the pattern of errors is that you only have so many object files, basically, so you're forced to rely on your approximate number system for magnitudes beyond 4. So a kind of problem with this view is that it's somewhat post hoc. So the basis for this project is trying to see if we can understand number psychophysics by modeling perceptual limitations. And so the proposal that we take is that number psychophysics can actually be understood mostly, if not completely, as a reflection of limited perceptual capacity. Specifically, that one's ability to individuate and represent objects in a scene ends up leading to subitizing and estimation and underestimation and all of these biases and patterns that you observe in numerical estimation. And a key prediction, which I'll focus on in this talk, is that we can actually derive these properties of number psychophysics by looking at how people perform on a spatial memory task, on a totally non-numerical spatial memory task. So the first part of this is a model of spatial memory, and it's super simple, but captures kind of the essence of the problem. So we suppose that we have a grid. The world is just a bunch of different discrete locations. We observe some scene S, which is composed of some number of objects, which are in different locations. And the learner, or the viewer's job is to represent this scene as precisely as possible. And they do this, they represent it with scenes S prime. So they form beliefs about how likely any given possible scene was after viewing scene S. So I'm not going to go into the math, but basically there's 3 components that go into a constrained optimization problem, which will allow us to derive the kind of optimal psychophysical function. So the first is that we assume that the viewer has prior beliefs about how likely different scenes are, and that's a function of the number of objects. So there's been previous work showing that the need frequency of number is proportional to 1 over n squared. And then there's a term here for the number of ways to represent n objects in a grid with m cells. There's a loss function, which just says you want to represent the scene as accurately as possible. And the third is an information capacity bound, which says that there's limits on your ability to update your beliefs. So you have some prior, and you can only diverge from it by so much. And you can put all these things into a constrained optimization problem and solve and find the optimal psychophysical function, which is this guy right here, which I'm not going to go into too much, but I will show you kind of some predictions that it makes. So we assume that, just for the sake of clarity, we're just going to assume that there's only 4 possible locations in the world. We see some scene S, and we can look at what the model says about how beliefs should change as a function of the information capacity bound. So we start off representing scenes as the prior when we have no bits of information. And as the information capacity increases, so if, for example, you have more time to view the scene, then the representation will become increasingly vertical. So you'll be able to represent the true scene with increasing fidelity, and scenes, also scenes that are kind of okay approximations of it, will get upweighted initially. So the kind of key idea is that, of course, there's implicit beliefs about the number of objects here, right? So these all have 1 object in them. These all have 2 objects in them. And so you can sum, and you can look at how beliefs about the number of objects in the scene change as a function of the information capacity bound. So the probability of there being 3 objects is just the sum of all of these guys right here. And so this gets eventually upweighted. Okay. So we ran a spatial memory experiment to test people's spatial memory and see if the kind of spatial memory that we observe is will allow us to predict number psychophysics. So we ran a change localization task on a 7x7 grid, and on each trial some of the cells were filled and then disappeared and reappeared with a change, and the participant's job was to click on the cell that changed. So what this looked like was there was a grid, some of the cells were filled, it was noise masked, and then participants were told to click the cell that changed. So I think that was this one. Okay, so we can now just jump to the results of this experiment, the kind of key finding. So the key finding here on the x-axis is the number of objects in the scene, and on the y-axis is the accuracy. So the model is the lines here, which is fitted to the humans, and the points here are human data. So what you can see is that at short amounts of time, when the display was only flashed for very brief amounts of time, both people in the model are, kind of quickly inaccurate, even inaccurate with scenes that don't have that many objects in them. But as the as the amount of time increased, people saturated in their performance and were very accurate. But even at 450 milliseconds to view the scene, their performance quickly dropped off beyond that. So we can actually take people's performance on this task and use it to guide what we think number psychophysics should look like based on their performance, if it was all just a function of spatial memory. So these curves are what the model predicts about what people's number psychophysics should look like. So at 50 milliseconds, the model predicts that people should only be able to precisely estimate one, maybe two things, not quite two, and that they should be kind of show this increasing amount of noise at larger quantities and be biased to underestimate. And as they have more time, they should be able to represent about 3, maybe not quite 4 objects precisely, and then have somewhat more precise representations of larger quantities, but still show this kind of increasing error with a bias towards underestimating. So the final thing that we can just look at from the implied number psychophysics from the spatial memory task is that we can see that the model predicts that they should be biased towards underestimating larger quantities, maybe slightly overestimating smaller quantities at short times. And they should show kind of no error given enough time for 3, maybe 4 objects, and then beyond that show a linearly scaling variability in their estimates. And so this is obviously very closely aligned with what we already know about number psychophysics. But just to be able to compare within this kind of setup, we ran a analogous numerical estimation task on a 7x7 grid with different exposure times. So again, they were shown a grid, some of the cells were filled, and they were asked this time how many cells were filled. So we can just jump to the results. So what we see is, so again, the model is the lines and human data is the points. So what we see is a bias towards underestimation that disappears with greater exposure time. And this is reflected both in human data and the model's predictions. And a propensity to, the ability to precisely represent scenes with few, or estimate the number of objects in scenes with few objects in them given enough time. But if not given enough time, even scenes with only a couple objects in them will be not very precisely represented. We'll show some imprecision in estimation. This is mean estimates, and this is the standard deviation of estimates as a function of quantity. So to summarize, we used a model of visual memory or spatial memory that we used to explain key psychophysical properties of number. So this model, this kind of view, explains why there's a four-item limit on exactness, why noise increases roughly linearly with magnitude above 4 items, why people tend to underestimate larger quantities, and why response distributions are roughly normally distributed. And this is all without positing two different systems. This is just kind of derived from thinking about constraints on visual perception. So again, this is another way of saying this is that we can derive properties of number psychophysics by assuming that visual memory efficiently allocates resources, and that discontinuous behavior for small and large numerosities can be explained by a single system. And this implies that the approximate number system may not be an analog magnitude system at all, and because the model represents discrete individual objects. And with that, thank you.